We're continuing on here with this topic, and now we're getting into what are called deBroglie, and it looks like deBroglie, but deBroglie waves, basically matter waves. Now, before we had that light acted as both a particle and a wave, and it was deBroglie that came along in his PhD thesis, I believe, and showed that, or showed that how matter could be treated as both a particle and a wave. So something like an electron, not only did it have this particle nature to it, which we all knew about, but it also had a wave nature to it. Now, we already known that the energy of an electron is quantized, and in particular the angular momentum of an electron, is quantized in discrete quantities, right? It's quantized to h over 2 pi. Sometimes you might see this as just h bar. It's the reduced Planck's constant because this h over 2 pi shows up quite a lot, not just the Planck's constant on its own, but h bar. So you might one day need to know that. You don't need to know it here, but h bar would be this h over 2 pi. And if the angular momentum is quantized to that, then basically we can say if we have the mass of an electron times its velocity times its radius, that's its angular momentum, is going to then be equal to some integer number n times that h over 2 pi. Okay? And we can replace the mv with p, because remember, p equals mv. And then if you multiply this 2 pi over, you get 2 pi r, and the circumference of a circle is 2 pi r. So the circumference of the radius is in here too. Multiply that 2 pi over, replace that with p, and you get that the momentum of the electron times its the circumference of its orbit is equal to nh. Okay, and so at this point we need to go back, and I believe I talked about this way back when I talked about this, but when you talk about harmonics on a string, standing waves on strings, well, the idea is that if electrons have a wavelength, then basically they can start to form their own harmonics. And this explains why we have these discretized, why we have these quantized energy levels, because what happens is, just like the standing wave on a string, when you had the wave going in, right, the wave would be sent down the string, and we would get these these standing waves, one that would look like this as the wave bounced back and forth and basically interfered with itself. And if you have to go back and take a look at that, and we would get these different standing waves that would look like that, and then you'd get one that had 3 on it on the same wavelength here. Well, if you take these and you try to wrap them around from just a linear problem on a string, but wrap them out to like a 3-dimensional wave, if you can kind of imagine it. If you wrap it around into a 3-dimensional kind of thing, what you end up basically getting is the interference of the electron as it goes around the nucleus. It basically interferes with itself, just like these standing waves did, and you get these discrete orbitals. And so something like this might correspond to an s orbital, where you get that, that nice spherical orbital, and then something like this would be like that d shell orbital, where it was like those kind of barbell looking ones, and then you'd have that other one sticking off like that, all orthogonal to each other. And so you get these quantizations occurring and giving you these discrete orbitals. So why can't an electron exist at slightly outside this s orbital? Because if it did that, it would go around essentially and interfere with itself destructively. It's kind of like how here you couldn't have you couldn't get waves that would exist on the string, standing waves that would exist on the string and be stable in between these. When we try doing it, you get just a jumbled mess at any frequency that's between these. So the electrons could only exist at certain wavelengths. So rather than varying the frequency of these, you vary basically the length of the string until you get different standing waves. but only certain ones could exist where you would get that harmonic, that standing wave for the electron in orbit around it. And if we do that, we can basically say then if we're looking at one of these, we can get that C, we can get from this, we can get that C is equal to N lambda, right? And then from there, you take this. This is because sorry, I wasn't very clear on that. This comes from the idea that the path, the circumference of the electrons in orbit has to be an integer multiple of the wavelength, so that it has that positive. It has that positive interference. It doesn't have that destructive interference. This gives you constructive interference for the wave. So this quantizes these circumferences that can be done here, right? So I maybe shouldn't have written that right there, but that is the quantization of the orbitals, right, where they can only fit in these certain orbitals. It has to be an integer multiple the wavelength does, an integer number of wavelengths going around in the orbital to interfere with itself. And if we substitute this into the equation above, you get that P in lambda is equal to NH, and the n's will cancel, right? And then you get that P is equal to H over lambda. And this is the deBroglie wavelength, or deBroglie. This is your deBroglie wavelength, and it's based on the momentum of the particle. And this then turns out to apply to more than just electrons, but it's basically the momentum of the particle is equal to Planck's constant over the wavelength. So the momentum of the particle, as far as this is concerned, is going to be inversely proportional to the wavelength, which should make sense because the bigger the wavelength gets, the lower in energy it becomes. The lower in energy it becomes, the lower, or the bigger the wavelength, the bigger the wavelength, the lower in energy, the lower in energy, the lower the momentum. If the wavelength is really small, you have a very high frequency, you have a very high energy, right, from before with our E equals HF. A very high frequency means a very low wavelength, which means high energy and high momentum. So it makes sense that the momentum and the wavelength would be inversely proportional to it, but this wavelength here is our deBroglie wavelength. Okay? And now, going on beyond that is, what exactly is this wavelength? What does it actually mean? Well, does it mean that if we zoom in real close on an electron flying across the room, we'd see the electron going and, going in some sort of wave and oscillating up and down? And I think originally, people kind of thought along lines, but ultimately, that isn't the case. So let's just erase that out of there. What it appears to be, the interpretation of it now, is this wavelength is what is called it's called a probability wave. Okay, and I know this doesn't make a lot of sense because this is really getting into quantum mechanics now, but it's a probability wave. Okay, and what this is it's the wave nature of it is this wave that tells you how likely you are to find it at any place. So if you have this probability wave going something like that, right, whatever it happens to be, whatever shape it happens to be, what you would do is you would look at across this and you'd look how high is this. So if I went to look, if this was the wave for an electron, I would be most likely to find it wherever this was highest, and I'd be unlikely to find it where it was lowest. So I'd be more likely to find it here than here, and I'd be less likely to find it here where it's low than here next to it where it's high. So if I produced a million particles in an identical way, it's not just one particle. I can't take and look at one electron, and every time I look at it, it just flips around between these positions. What it would be is if I produced like a million identical electron setups, a million of these particles in the same exact way, and then I went and looked at each of them, I would find a distribution that most of them, like if I started every time I found one, I marked on here an X where it was. I would find that most of them would be here, a few of them would be here and here and here, and occasionally I'd find one here, and I'd find a bunch here and some here. And if I then plotted out where I kept finding everything, it'd be almost like a bar graph, and it would take this shape for everywhere I was finding all of these electrons in here, and it would basically, fill up this shape. So the probability wave just tells you how likely you are to actually find it in there. So this wave nature of it is a little hard to think of, but it's a probability type of wave nature. It's not the actual particle itself going along and making itself into a wave and looking like an ocean wave or something like that as it goes by. So the thing we contain this probability wave in is something called the Schrodinger equation. It's the Schrodinger equation. I don't want to write that whole thing out, but basically it's psi, the Greek letter psi, and this is basically called the wave function of it. Okay, the wave function. Now, the way you need to look at this is just a regular old function of position or something. Is usually what people look at. But in reality, if you get into taking quantum mechanics, what you have here is this psi is basically this vector thing. It's this vector function thing, right? This psi, it's this vector, and this part here about it being a vector is a little beyond what you need to know, but I think it helps to kind of identify it. And the idea is, say you want to know the position particle. This psi contains all the information you need to know about its position, its momentum, its energy, and all this kind of stuff that you would need to know about this particle. So you get this psi, and if you want to know what its position is or where you're likely to find it, what you do is you take and you project it into a position space, right? So an x, y, z space or whatever it is, all these positions, right? X, that could be x, that could be y. And then as you project psi down into that, we'll do that with like a light green, you project psi down onto this position space, right? What you can do is look at the length of the component of it in the x direction and the length of its component in the y direction, let's say. Really, it wouldn't be in the y direction, but it would be the length of its component at this position. And that length of that component, the longer it is here, and the way I've drawn this, you'd be more likely to find it here than here. And the length of it would be proportional. The length of these projected, you project it in the space, take the length of the components, and the lengths of these components tell you how likely you are to find it at those positions. And it would be more than just x and y. It would be x, y, z, q, r, k. It would be basically an infinite number of these positions in here. So you project it down on the position space, and then you would look at it. When I say look at it, I mean you do this mathematically, because obviously I can't draw an infinite number of positions out here. And then I would take this same psi, like say I wanted to know momentum or something, right? Like say I wanted to know its momentum, then I would project it over. I'd have some other space over here with different potential momentums, an infinite number of them, and I'd project this down onto this momentum space, and I have this projection of psi into this momentum space, and then I'd find the length of it, its components in all these different momentum directions, like do my finger in quotes kind of momentum directions, and that would tell me how likely it was to have all these different momentums. And so anything you want to know, you just take this crazy psi vector function thing, you project it into a different space, and then you look at how it looks in that space. How long are its components in different places? And that tells you the probability of finding it. I'm sorry. You take, I keep saying this psi. It's actually not just psi. Part of this projection, I'll talk about in a second. It's a little more complicated than this. You have to actually do a square of it. But basically, the projection of it in one of these spaces, you look at how long its component is for these different possible momentums or different possible positions, and it'll tell you then. So momentum 1, momentum 2, this could be like x1 and x2 instead of x and y. But anyway, so if I looked over here, if say this was a position wave, what I would do is I'd project psi into it, and when I project it, it would give me it would give me out something kind of like this, not exactly this, and I'll talk about that in a second. But it would give me a probability type of thing in here, and the further it was away from the axis, the projection of it would be this. So like maybe this was the x position, or this was the y or x1 position, or that's the momentum. There's momentum 1, and you basically have these infinite number of these momentums all through here. And I'm probably going way over what I need to here at this moment, but I wanted you to get some idea of what this psi really was. It's this abstract vector thing that you project into different spaces, and then it tells you, based on how it is in that space, how likely you are to find it in different positions. And I think that's a little important when we start talking about the uncertainty principle, which will be in my next video, not in this one, to kind of know about this psi being projected into different spaces, because it'll help kind of understanding that part. So, but remember, with all this stuff, you kind of just have to know how to do it mathematically. There is no actual great way to visualize it in your head. I'm doing my best to come up with something here that kind of visualizes it for, but in reality this would be an infinite number of positions, not just x and y, an infinite number of momentums, and then you take an infinite number of these and you'd get this kind of smooth curve out here where the height of it would be the length of its projection for each position or each momentum. And it just depends, did you project psi into position or did you project it into momentum, and you'd get a different wave doing each one. An infinite number of little components that it would have in all these different possible directions. So anyway, I'm blabbering on there about this, but I kind of wanted you to have some idea again, so that when we get to the uncertainty principle, it might make a little more sense. In reality, what you do after you project it into these spaces is you then have to square it. So what you get is that the probability of finding that particle is equal to that wave function projected into whatever you're going to do. Most commonly at early levels, it's into the x position, so it gives you psi as a function of x, and you take that and you square it, and that times your volume that it could be in gives you this. Or you do the other version here. If you're that version, you kind of basically have to know this idea here. Or you divide both sides by this and you get the probability density, which is your probability per volume, right? Because that's what densities are, they're per volume. Your probability density would be this psi squared. So give you an example of this. One is the particle in a box. If you have it confined into some well, this would be like, this is the one-dimensional version of confining an electron or something in orbit around a nucleus. You would have it confined in this box, and the first wave function would look something like, let's just do this color here, would look something like this, and then the second function, the second wave function when you project it, I'm not doing this to scale, would look something like that, and then the third one would look something like this, and it kind of looks like those harmonics from before, right? And again, I'm not worrying about how high I go with these, I'm just trying to show you the basic shape. And then you would take these wave functions, so this would be projected into a position space, because this is a physical position well. And so what this tells you isn't much, but if you take and square it. So if we have our well again, right, you take those positions and you square them, right? And so your first one gets squared and it looks like that, and then the yellow one, you square it, it makes all these negative ones up to positive, and then these would actually be your probability densities of where you would find this thing. And I know they're kind of crazy shaped. Like if you look here for the yellow one, you have 0 chance of ever finding it right in the middle in that second energy level. This would be like that second orbital. It's a higher energy than the first one. And then this green one, you have no chance of finding these two positions either, and you're very likely to find it here and here and here. And so you just look at how high it is at any position. You want to know how likely you are to find it here. You just go up here to how high it is and you look at it. Okay? I'm again probably blabbering on about this, but essentially psi squared. Psi squared gives you your probability density, not just the wave function, but the wave function squared. And that has a lot to do with that this wave function can actually be complex. It can have imaginary numbers and stuff in it. So you have to actually square it out to get it into something that's real, which means it's then a measurable thing, because imaginary terms are not actual real measurable things. All right? So I'll stop blabbering on about that, but I will come back to these pictures here in the next video as I talk about something called tunneling when we get to that. So you'll see these again in the next video. All right, that's all.